Thank you, Suzana. Okay, am I audible to everyone?
Yep.
Great. Yeah, okay. Really excited to be here and let's dive in. Yeah, quick self-introduction. I'm Alex and I used to live in Germany for 9 years before I moved to Japan 8 years ago. And I'm currently an AI cloud and AI specialist at Microsoft Tokyo. And before that, I've also been, well, a software engineer and also a graphic designer. That's like decades ago, journalist. And also I play the cello because my dad does that. And yeah, so GPT-OSS, that's the first reasoning open weight model from OpenAI. And I was really, really excited to see it dropped. And basically, it's really nice to see how they implement it. So today I will also refer to their code from time to time. And yeah, so let's start with the overview of the model and was released just a couple weeks ago. And there are two size variants. 120B has actually 116.8 billion parameters, and the 20B has 20.9 billion. And both are a mixture of experts, which means they actually have much less active parameters. And so 5.1 for the 120B, the big one, and 3.6 billion for the small ones. And they have the same context length, pretty big. And also very exciting thing is they had some very smart quantization. So the big model can actually run on a single 80 gigabytes VRAM GPU, which is very rare for a model of this size. And also the smaller one, you can actually run it locally. I actually got it running on my laptop on the night it was released. And the performance is even more exciting. Like they have showed their benchmarks, and in the reasoning benchmarks, the big one has near O4 mini performance, which is their up-to-date mini version of reasoning model. And the smaller one also matched last generation O3 mini performance. And well, for modality, the models are text only, and they have actually post-trained it to already support agentic usage. And also the reasoning part, they actually give us the full train of thought, which is very interesting and very nice. Although I tested and I asked it questions in Japanese, and the answer is in Japanese, but the chain of thoughts are all in English, which is quite funny. So the architecture, yeah, well, we see that it's actually a pretty standard sort of LLM architecture. You have transform blocks, like multiple layers of transform blocks, and each transform layer will include the attention block and not FFN, but MOE block is the other part of the transformer layer. And in the MOE part, they implement the activation in Swiglu. And also they said it's actually a small unconventional implementation because they use clamping and also a residual connection there. And the MOE parts are quantized to MXFP4 format during post-training, where the weights are in 4.25 bits per parameter. And this is also why the model can run in such small memory footprint, because the memory parts are generally responsible for like 90% of the parameter count. This quantization actually is the hero that gives us this model in a single GPU or in our edge device. And the architecture itself, like I said, pretty standard for a model for modern LLM. And they will actually mainly be diving into the attention block. But before that, one slide for the normalization. So the deep neural network will have stacks of dozens or hundreds of layers. And without normalization, the activation can get explode or vanish. And so that's why we always need normalization. And there are conventionally or traditionally layer norm was used in the original transformer in 2017. And the layer norm just simply recenter it to the mean of the whole feature vector and then rescale it to unit variance and then rescale with some learned parameters. And nowadays, everyone uses RMS norm, the root mean square norm. This hypothesizes that layer norm's success is mainly due to the rescaling, not the recentering. So it removed the mean subtraction part. This makes the computation somewhat cheaper, and the quality is similar to layer norm. This is first popularized when Llama adopted this, and now it is basically everyone's using RMS norm. And also another topic is about the placement of the normalization. In the initial transformer, the original transformer decoder part, we can see it's like on the right side, they use post norm. And we can see that they put the layer norm after the residue connection. And this is, in this way, the residue output is also normalized. So each layer's output is more stable. But that's probably the only good thing we can say about that. Pre-norm, on the other hand, well, post-norm needs careful learning rate warm up. And also the gradient flow can vanish. So it is not very good for training stability of very deep models. And on the other hand, the pre-norm, that is the norm of modern LLMs. It is much more stable for deep models, and it's also less sensitive to warm up or learning rate schedules. You can see that it's just put the norm in front of both the attention and also in the MOE block, it puts it in front of the MOE or FFM. And also some models use both pre and post norm. And yeah, I think, yeah, why not? It's just a little bit of small compute overhead. And yeah, let's get into the algorithm gems of the attention block. I'm gonna go through 5 of them on GQA, which give us smaller KV cache, and SWA sliding window attention, which also is very good for efficiency and scalability. And then Y, it's a very interesting design that they alternate dense, which is the GQA only attention layer, and sliding window layers. And also there is this, they added this learned bias to their attention. And at the end, how they do positional encoding with rope, and also how they extend rope with yarn to support a very stable long context. Yeah, they have what, 128K, or actually 131,000. That's pretty long for open source models, especially. So, First, GQA, grouped query attention. The original transformer introduced multi-head attention, so each query has one key value pair heads to it, and it achieves very high quality, but it's also very expensive in compute and memory. So there are several multi-head attention variants came along after it, aiming to improve the efficiency. And Google has introduced multi-query attention, the one on the right, and in 2019. So not far, not so long after the original transformer. And MQA shares only one KV head across all the query heads. And this is very efficient for inference, but it also brings noticeable quality drop. And also you can't really use that in training. And in 2023, also from Google, and they proposed group query attention. This actually hit the sweet spot between MHA and MQA. It splits the query head into groups, and then each group will share one set of KV heads. In this way, we reduce a lot of KV parameters, and the model train more efficiently and also need much less KV cache at inference. But the quality is really close to MHA. And you can see the code snippets here, how GPT-OSS implemented it. In the config, they set the number of attention heads, which is actually the query heads, to 64. So they have 64 heads in total, and they have 8 sets of KV heads, meaning each group, there are 8 groups, and each group will share their KV head. And in the scale.product attention function here, we can see that the queries come in with an extra dimension, the query multiplier, and then the K and V will be added this X axis and then expand along this axis to be shared with the group of the queries. The next one is SWA, sliding window attention. Sliding window attention is a local sparse self-attention pattern where each token will attend only to a fixed-sized neighboring window of tokens around it instead of all the other tokens like the normal attention. And in causal LLMs, so basically autoregressive ones, it will just attend to the small window of tokens before it. And yeah, this was the origin of this is in 2020, Allen Institute for AI published Longformer, and that combined a dilated sliding window. That means it's not cramped together. It could be jumping ahead, and with optional global tokens to achieve linear scaling on long documents. And in 2021, Google Research published Big Bird, which used a sliding window plus some random tokens and global tokens. So this schema also showed expressivity close to full attention. And Mistral 7B, released in 2023, adopted SWA, because it's very popular. And so we can see the vanilla attention has squared, like quadratic complexity. And the sliding window attention has basically linear because the window size W is normally much smaller than the context length. And in the case of GPT-OSS, they have the max context length of 128K, and their window size is 128. That means in each layer, in the SWA layer, each SWA layer is 1,000 times cheaper than its dense layer counterparts at max length, of course. And it's actually pretty easy to understand the implementation. They just, after the causal mask, they check if it's currently a sliding window layer. And if it is, then they will apply an additional SWA mask to it. And they have published in their model card that this pattern is following GPT-3. So I didn't know, well, I don't think anyone knows before that GPT-3 has this alternating dense and SWA layer architecture design. And we just talk about SWA, it saves resource and put focus on local information. And why do they do this alternating? Because in every even layer where the sliding window is there, the model will pay close attention to only the most recent information, the local one. And so we still need a global awareness. And that's why they will have the next layer to be the dense layer. And so basically, then the model can switch back to attend to global information after they have paid attention in the last layer to just the most latest for local information. So I like to think about it like when I'm reading, and I will read the current paragraph very closely, but sometimes from time to time, I would also skim the whole document to see what I've read before to still get the global awareness. And GPT-OSS does this systematically. So it basically local, global, local, global. So I guess this is a pretty healthy mix. And then we have the context lens extension part. Oh, sorry, I'm seeing the wrong slide. Okay, so in the attention block, there is another interesting part is they added a learned bias, also called attention sink there. So this is what they wrote also in the model card. And so each attention head has a learned bias in the denominator of the softmax, similar to off by one attention and attention sinks, which enables the attention mechanism to pay no attention to any tokens. So what is off by one attention and what is attention sink? And how do they help GPT-OSS enable the model to pay no attention to any tokens? Also, why do we need this in the first place? So let's first look at off by one attention. It was from Ivan Miller, who's currently working at Anthropic. And this is a very interesting article he wrote. And he argued in standard softmax, every attention head must assign a probability mass to all the tokens, and all the probabilities will need to sum to 1. But we know that each attention head, after all this training and learning, will be specialized in certain ways to understand what's in the token or embedding. And sometimes for some attention head specialty, there is simply no token that they should be focused on. So Ivan Miller suggested to append an extra dummy logit to the softmax denominator and then remove it after softmax. With this, the attention head can allocate some attention mass to no token, the dummy token, and this will effectively let the attention head stay quiet when it has nothing useful to contribute. And on the right side, what is attention sink? Attention sink was proposed also in 2023 by Xiao, and it was actually meant for applications with infinite or very long streaming inputs that will flow into attention models. And so naturally, the model cannot attend to the whole input because it can be infinite and it just keeps coming. And also, there will not be enough memory for KB cache of the whole very long streaming or the whole infinite long context. And so naturally, such application will need to implement windowed attention. But this will fail if the text learns surpasses their KV cache still. And Xiao and his team found out, well, it's actually empirical, and they have done a lot of experiments. And they found out that keeping the KV of initial tokens in the cache, namely using them as sync tokens and assign them some pretty big scores. So every new step would need to pay some attention to them. In this way, the new step attempts will be attending not only to the most recent window, but also these initial tokens. And this can largely recover the performance of the windowed attention. So in other words, the sync tokens act like an anchor so that the model has some stable reference points. Both these two methods help attention heads from latching onto irrelevant tokens. The off-by-one gives attention heads a way to ignore all tokens altogether sometimes when it fits, while attention sync keeps some tokens always visible as the anchor. And we see in this code snippets down here, GPT-OSS implementation is closer to off-by-one. And it introduced this sync as a learnable parameter. And then in the attention calculation, it adds the sync concat basically to the QK, and then they do the softmax, and then they remove it. So this let the model learn to ignore noise. And the context learns extension part, rope and positional encoding, and yarn for context learns extension. Well, first, why do we need positional encoding or embedding? Because self-attention is permutation invariant, meaning if we say Andy pets a dog or a dog pets Andy, it's all the same to attention, to self-attention, because they are all the same tokens getting attended to. So each query token will attend to it simultaneously. And so transformers have no built-in notion of word order or distance. And the original transformer used sinusoidal position encoding, which encodes each token position as a unique vector of sines and cosines at different frequencies. And it then adds this to the input embeddings. This is essentially absolute position encoding, though the model can also learn some relative order and distance from the relative offsets. And rope also use sines and cosines at different frequencies to map the token positions. But unlike sinusoidal position encoding, rope is not adding them to the input. It uses them in a rotation matrix that is then applied to each query and key. And the rotation angle is proportional to the token position. So when we compute dot product of tokens at two positions, naturally we capture the relative position information because it's just how the angle in the 2D dimension works. And this lets the model capture word order and distance information more straightforwardly, and it also enables sequence-learned extrapolation. Also, since rope is not adding anything to the input embedding, it preserves the norm of query and key vectors. So this is also good for training stability. And yeah, so because of all these benefits, so basically it becomes the de facto positional encoding method for modern LLMs. And yarn is yet another rope extension we know from the name, so it works with rope together. And why is yarn needed? Well, rope can degrade at long contexts where the high frequency dimensions wrap around too quickly. And especially if you try to extend sequence learns way beyond what it has seen during training. And so ever since rope was popularized, there has been a lot of community experiments to scale it. For example, PI, position interpolation, simply computes a scaling factor between the new longer context and the old context learns, and then use it to compress the position space uniformly. And also NTK, neurotangent kernel aware scaling. This one scales the frequency, not the position. And according to the embedding dimension, the scaling is not uniformly. Well, this table is actually provided in Young's paper, and the author actually did some great comparison of them. So rope's frequency design is multi-scale across the whole embedding dimensions. Well, the high frequencies will capture fine-grained positional relationships like local attention focus, and then low frequency part will capture more coarse-grained positional information like for global focus. So that's why the PI naive scaling won't work, because it hurts all frequencies uniformly, and especially at the high frequency part, it overcompresses it. So we lose a lot of the fine-grained local attention information. What Yang proposed is it improves PI and NTK by using NTK by part scaling. Simply, it interpolates low frequency range, meaning stretch it, scale it. And for the high frequency part, it just keep it intact. They call it extrapolation. And also it adds an attention scaling temperature to compensate for the rescaled frequencies, keeping the attention sharp and stable at long context. So, and last, I'd like to also take a look at the training part. The pre-training was done on text-only data, trillions of tokens, and mainly on STEM coding general knowledge data. And also for safety, they applied the CBRN filter that they have used when training GPT-4o. The knowledge cutoff is June 2024, about a year ago. And the training has 2 million GPU H100 GPU hours for the big one, and 10 times less for the smaller one. They didn't disclose if they trained both from scratch or if they, like DeepSeek has disclosed, if they distilled the small one from the large one. And for framework, they use PyTorch with expert optimized Triton kernels, and also use flash attention for memory efficiency and accelerate the training. And the post-training part is even more interesting. They post-train with train of thought reinforcement learning, which they have also used in their closed source models like O3. And they mentioned that because of this same technique, the models might have similar character there. And their post-training is for reasoning and tool use. And they mentioned this new Harmony chat format for that. And in that format, they have different roles: system, developer, user, assistant, and tools. And they also tell us the conflict resolution hierarchy. So basically, if you are the user, you can't really define the developer or the system, but you can order the assistant. And this chat format, the Harmony chat format, also provide 3 output channels. And the final channel is the one that's supposed to be shown to the end user as the final answer. And there is this analysis channel, which gives us the full chain of thought there. And they also told us that this part is not adhering to the same safety standard as the final messages, which means it would be really interesting if we dig into the chain of thought from time to time. And there's also this commentary channel, which is supposed to be used for trigger function tool call, especially for custom developer functions. But sometimes they mention that normally the built-in tool, which we can see here in the agentic tool use part, and the browser tool and Python tool they provide, they normally should be in the analysis channel, but sometimes they can also get into the commentaries channel. And for variable reasoning effort part, they provide 3 levels: low, medium, and high. And this is configured in system prompt with the keyword like reasoning and low. And as the reasoning level increases, they say that the chain of thought learns increase. So this is interesting, like thinking longer is thinking deeper. Is it really? Or we will find out. And also for agentic tool use, and they provide a browsing tool which has search and open functions to interact with the web, and also a Python tool to write code. And also the developer can define their custom tools, which is just to provide the function schema in developer message. The schema should follow their closed source models schema when you're using OpenAI's like GPT models. Okay, so that's all of our deep dive contents that I've prepared, and I think we have a little bit time for some questions.